Hello, my name is Tim Matson, and I'm going to talk about some quantitative data we have measuring just how popular OpenMP is. And this comes from a study with a team that we worked with from Israel, Gal Oren and his team, reporting on a talk and a paper at the IEEE HPEC conference. So the link to the paper itself is at the bottom of this slide. So check it out. So I have a little secret to tell you. The fact of the matter is, people like me who work on programming models, we really don't know how much our models are used. We tend to overestimate them. It's like the children of Lake Wobegon, that, all programming models are above average. But we really don't know. We can count downloads, we can get stars on GitHub, but we basically just have rough guesstimates and anecdote. And the reason is because it's expensive. It's hard to get hard quantitative data on model usage. So we just trust our guts. One of the few sources of hard data comes from a study from the National Energy Research Supercomputing Center, or Nersc. So Helen He led this effort with some of her colleagues and reported on it at an OpenMP Con in 2015. And so it shows that on their machines, now remember, their machines at this time were large, 5,000, 6,000 node machines, emphasizing the CPU. So do not interpret this data to think we're studying the GPU. It really emphasizes large CPU-based systems. And what you see is that well over half their programs are Fortran, about a third are C++, and about a third are a little under a third are C. And this can add up to more than 100% because you have multi-language applications. The Python usage is up over 20%, but if you talk to them at Nersc, most of the Python usage is workflow management, not the heavy lifting in the computing. MPI, well, over 90%, which is not surprising because that's how you're going to take advantage of these multi-node machines. But look at OpenMP hanging in there. 40% of their workloads were using OpenMP. Of the time in their computing, we're using OpenMP. Now, we talk about the standard model in high-performance computing as MPI plus X, MPI between nodes and X on a node. And you see, analyzing the applications in the Nersc data, people running at Nersc, pretty much 50% of X is OpenMP. The next most popular would be CUDA, which is pretty cool given that these are not predominantly GPU-based machines. But 50% OpenMP, pretty good, well behind MPI, but still quite good. Now this study though was 2015, so let's face it, we're 2023 right now, it's a little old. And it's also focused just on Nersc, a big DOE-funded supercomputing center. I want to know about something more up to date. I want to know about more generally, not just a supercomputing center, but just parallel computing more generally. That's really what I would like to get data. And can we find that? Well, enter stage left. Gal Oren and his team from Israel. I met them a year or so ago, and they were talking to me about their line of research to explore constructing large language models to be used in parallelizing code. And what I loved about their idea is that if you train your model on the sort of data that maps the scope you wish to apply it to, that you can have smaller models that don't cost an arm and a leg to train. So they got some help from Google, and they used BigQuery, and they collected data, and they call that data set HPC corpus to support this. Now HPC corpus, I have the actual query that they use through BigQuery is on the right side of this slide. But I'm going to mostly focus just on that table to give you an idea of how large this sample is. 144,000 C repositories, C containing repositories, 150,000 C++ containing repositories, 3,600 Fortran containing repositories. We're talking millions and millions of files. This is a pretty significant sampling of everything you can find on GitHub. And they put timestamps on these based on when were they last updated. So the final update. And they looked at cases where that final update happened between 2012 and 2023. So I can't emphasize enough that their goal in creating HPC corpus was to build a data set for training models. But we realized when I was talking with them that, gee, it wasn't the goal, but we can use this to get quantitative data on programming model usage. And that's pretty cool. Now, they looked at files with suffixes .c, .cpp, .f90, .f, .h, .f95, .f03, .cxx. Now, I want to be very, very clear to people interested in GPUs and my good friends at NVIDIA that we did not look at files with suffix .cu, .cuf. So we picked up CUDA when there would be an include file or a memory access routine in a C or Fortran file. So we did get a lot of data on CUDA, but we undersampled because we weren't looking at .cu and .cuf suffixes, and those are the ones specific to CUDA. So I like to point that out because I don't want to mislead. But a lot of files, and you can see how it broke down by suffix. So, okay, how popular is OpenMP? And what you can see, remember these dates show the date of the last update to the repository. And we're plotting the number of repositories on a log scale. And you can see that consistently from 2013 on, OpenMP is number one. Think about that. Let it settle in a little bit. OpenMP is number one. We beat MPI. Haha, MPI, we win. OpenCL is surprisingly coming in for much of that at number three. Even with our undersampling, we see quite a bit of CUDA, which I find very interesting. And TBB is way down. Remember, this is a log scale. So it's way down compared to the big four. So very interesting, though, that CUDA, even though we didn't sample .cu, .cuf files, CUDA came in pretty darn well. But OpenMP rules. Don't forget that. OpenMP rules. Now, there is that dip around the middle, and that kind of surprised me. So we hunted down and got some more data on number of repositories over time. And you can see there was a big spike in 2022 and, some dips around after 2018. So that dip is on par with some of these changes we see looking overall at GitHub. So I don't think it's really significant. But I like to cover everything, expose everything in the data set. Don't try and hide anything. That's my motto. So if we sum over time to just look at the repositories that are out there, not focusing on variation by last update, we get these aggregate numbers. And they show that OpenMP across GitHub is number one in 45% of the repositories. And we really beat MPI, which comes in at 27%. And then OpenCL makes a very respectable showing at 11%. And this is, at first I was really surprised because, I'd been conditioned from my buddies at the DOE supercomputing centers to think about MPI dominating. But remember, this is looking at GitHub overall. And that means that there are programs written for single laptops, programs written for single servers or small clusters, programs written outside scientific computing. In other words, it's more than just big system super scientific computing. We have a wider range of applications we're looking at. The OpenCL number was once again, I was surprised at how high that is. But remember, OpenCL, while it's not as heavily used in HPC, it is heavily used, we believe, in the client, computer games and places where you have a client interacting with computing on the GPU and visualization. So pretty excited about that number at 11%. And don't pay too much attention to that number at CUDA at 10%. We know we have a sampling error with CUDA. And so we can see here, focusing more on OpenMP, MPI, and MPI plus OpenMP, you can see steady growth across all of them, mirroring the rest of the data. But you also see significant growth, particularly moving out towards 2023, towards MPI plus X. But that doesn't compare to the marvelous spike we see in MPI out of 2023. So, just supports once again this conclusion that the use of OpenMP is really vigorous and growing rapidly. And so, very exciting. All right, let's talk about OpenMP specifications and the change in usage of OpenMP across the different specifications. So remember, in 2005 is when OpenMP version 2.5 came out, and that's the critical juncture in the history of OpenMP where we combined the C, C++, and Fortran specifications in a single document. Tasks were added in 2008, so that was version 3.0. In 4.0, we greatly expanded the usability of tasks by adding a depend clause. So now we could build direct acyclic graphs and just run those through the task mechanism. But also, that's when we added GPU constructs, SIMD constructs, and explicit control over non-uniform memory architectures. In 5.0 that came out in 2018, we added, too numerous to list, but a lot of enhancements to the GPU constructs, the NUMA constructs, and SIMD. We also added support for the C++ memory model in version 5.0. So what is interesting in this data here is we can track how quickly different specs are adopted. And what you see is as a new spec came out, pickup of new constructs happened quite rapidly. I'm excited. It took a little while longer for the 5.0 constructs to be picked up relative to the 4.0, but even there, they were picked up pretty darn quickly. Even as you move into 2023, you see, to my surprise, that, the specialized construct in 5.0, remember, which really focused on doing more with SIMD, doing more with NUMA, doing more with GPU, is up there catching up with, the original version 2.5 and version 3 of OpenMP. So that's pretty encouraging that people really are working with the new specs as they come out. So let's take a look at what constructs are used from OpenMP. It's probably kind of hard to read this in the video, but the PDF of these slides will be made available, and it's easier to read that vertical axis on this slide in the PDF. But what you see is that the standard multi-threading constructs, parallel, for, that sort of thing, are overwhelmingly very, very heavily used. And if you look at C, comparing threading versus vectorization versus GPU, you can see that, yeah, threading rules, not surprisingly, 75+% of what people are doing with OpenMP is threading. What surprised me, though, is if I go through and I compared what are people using in C++ from OpenMP, what are people using from C from OpenMP, you see that in C++, it may be 45% threading, but gosh, it's 35-ish% for GPU, vectorization 20%. So bravo to you C++ people. You are much, much more heavily using those, those newer ideas beyond just threading in OpenMP. So that's pretty darn cool. Now, a while back, myself, Helen Hay, and Alice Koenigas, we got together and we wrote a book called the OpenMP Common Core. And the OpenMP Common Core refers to the 21 constructs that we said, based on anecdote, based on our gut, but we asserted that most OpenMP programmers doing multi-threading, this is what they used, with these 21 constructs. And what's pretty cool is with the HPC corpus dataset, we can finally now test. Was our hunch, our gut impressions right? And I would say, for the most part, when you think about threading, yeah, it was right. We got it right. Hey, that's pretty cool. Because you can see that we mark with the red boxes the constructs that came out of the Common Core. And so, focusing just on for threading, you can see that, yeah, we pretty much got it right. But you can see places where, for threading again, the Common Core is all about just threading. Um, you can see there's some places where we missed it. And maybe when we do the next edition of that Common Core book, yeah, maybe it's time to go to, version 2.0 of the Common Core. So you can see that it's pretty important that we add task group and the depend clause to the Common Core. The depend is that feature, that clause that lets us build directed acyclic graphs of tasks. And then task group gives us more control over how the tasks, how we wait for the tasks to end. Collapse clearly needs to be added, and sections probably. I was really surprised at last private. Frankly, in my own, the own applications I think about, I don't see a lot of use for last private, but clearly I'm wrong because it's pretty heavily used. So at any rate, OpenMP is the #1 programming model in use today. Think about that. Let it sink it in. Yay, OpenMP. The other thing that surprised me in this data is the C++ community is much more aggressive about the newer architectural features that are addressed through OpenMP, the SIMD and the GPU constructs. I want to emphasize that the HPC corpus dataset we worked from is publicly available. There's the link. And I worked with them. I hope to keep working with them, but all credit for HPC corpus goes to Gal Oren and his team. They collected that on their own before we started working with them. So the next step is, well, what machine programming systems can we build using HPC corpus? That's pretty exciting, and I'm really looking forward to our ongoing work on that front. And then some point when I get time, what I really want to do is look at, okay, what constructs are used from MPI and what exactly is used from TBB. Just like we did in this study with OpenMP, we can do it to MPI and TBB. We kind of need to do that. So that's it. Thank you very much.